There are rules for designing databases in a relational model. These rules are called the rules of normalization, and we're going to study those next. But before we get into that, we have to understand one important concept, the concept of a functional dependency. So that's what we're going to talk about today. So what are functional dependencies? Functional dependencies are used in normalization to determine the goodness of a relational design. In other words, the functional dependencies are the key that will help us define what we call normal forms. And they're very important because if we know the functional dependencies, we will understand a lot about data redundancies and proper data modeling. These are constraints that derive from the meaning and the relationship of our data. And we have to look at our business problem to really determine if a functional dependency exists. So, our formal definition. A set of attributes X functionally determines a set of attributes Y if the value of X determines a unique value for Y. And you write a functional dependency like this, and we would read that as X functionally determines Y. Here is a table of zip codes for the beautiful city of Cherry Hill, New Jersey, home of the Cherry Hill Mall. And we can talk about functional dependencies. So we can ask ourselves whether city functionally determines the zip code. And the answer to this is, of course, no, because when I have a value of a city, I do not know definitively what the zip code is. It could be 08002, it could be 08003, it could be 08034. So if I know the city, I do not necessarily know the zip code because there's three choices. So there is no functional dependency here. However, if I go the other way and I look at these zip codes, does every zip code give me a particular city, one and only one city? And yes, 08002 gives me Cherry Hill. 08003 gives me Cherry Hill. 08034 gives me Cherry Hill. So our functional dependencies really work this way. Zip code functionally determines the city. And a way to say that is, given a zip code, I unequivocally know what the city is. There's no other choice. There's only one possible choice. Let's look at another example of functional dependencies. Here's a table of some automobiles. We have the state and the license plate number. We have the vehicle identification number, which is unique for every vehicle. We have a make and model of the vehicle. These are different cars. So keeping in mind that when you say a functional dependency and you say X functionally determines Y, that X is a set of attributes, so it could be something like X1, X2, and Y is also a set. That could be Y1, Y2, Y3, etc. So knowing that that's the form of a functional dependency, take a few moments and look at this slide and see if you can determine which functional dependencies you can find. So my first functional dependency is shown here. The state and the license plate number together will functionally determine the VIN, the make, and the model. That's because the state and the license plate number are unique to identify any automobile. And I need both the state and the license plate number because license plate numbers can repeat across multiple states. So that is our first functional dependency. For a state and a license plate, there's only one possible value for the VIN, only one possible value for the make and model of the car. Our second functional dependency is the VIN itself. The VIN is a unique vehicle identification number. So if I know the VIN, I most certainly know the make and the model of the car. I also know the state and the license plate because the VIN will point to one particular car. And here's one you might not have gotten. The model determines the make. Sometimes finding these hidden dependencies is the key to having a very good normalized database. So the car manufacturers never name models the same as other car manufacturers. There'll never be a Chevrolet Sentra or an Oldsmobile Elantra. So in this case, we can say with certainty that the model functionally determines the make. So every time I see Sentra, I know that it must be a Nissan and only a Nissan. If I see an Elantra, it must be a Hyundai and only a Hyundai. If I see a Trailblazer, it must be a Chevrolet and only a Chevrolet. So finding functional dependencies is really important, and it takes some time and it takes some thought. One of the challenges of identifying functional dependencies from data is that you cannot prove that a functional dependency exists. You can only assert that a functional dependency may exist. However, you can clearly demonstrate that a functional dependency does not exist if you see data that violates that functional dependency. So for example, if we were to look at these zip codes, you might assume that there's a functional dependency, that the city determines the zip code and the zip code functionally determines the city. But that's because we don't have complete data in this table. So with just one more row of data, now you can see that the functional dependency that the city determines the zip code is no longer true. When we add in Cherry Hill 08002, we can see that the city cannot be a determinant. And so therefore, it's important when you look at your data in a table to make assumptions about it. You can definitely show that a functional dependency does not exist. If we solve this table, you would know that city cannot functionally determine zip code. But you can't prove that a functional dependency does exist. For example, do we really know that a zip code can't be used for two cities? We can assume that, but without seeing the full data, we're not sure. This is why you have to look at the business rules for the data, ask a lot of questions to make sure that your functional dependencies are fully identified. You often have to go beyond the existing data that you're observing and ask several what-if questions. And that concludes our lesson on functional dependencies. I just wanted to end with a few definitions. When you see a functional dependency, such as X functionally determines Y, then X, the left-hand side, we call that the determinant, and Y on the right-hand side, we call that the determined. And you will use these words as we approach normalization in upcoming lectures.